Okay, so in the previous class for second order system, for the case of underdamped system means zeta is smaller than 1, we applied the input of impulse of S was 1, and we got that the solution of that system, mass spring damper, or any second order system, I mean, is like as A E minus zeta omega nt and sine omega dt. That's right. And we name this as the damped natural frequency, damped natural frequency omega d, damping ratio, and natural frequency. And we plotted that if this is our input, the impulse for the second order systems, you saw that we have a transient oscillation and then goes to follows the input. So by saying that, it says that the steady state error signal is 0 for this system. Okay. So now let's go into case B when the zeta is still underdamped, but the f of t is unit step, saying that it means that the f of s is 1 over s. When zeta is smaller than 1, system is underdamped, means that the poles of the system, P1 and P2, they are minus zeta omega n, as you know, plus minus I omega d. Means that you have a pair of complex conjugate poles on the left-hand side of the complex plane. Here we go. Here is real, here is imaginary, as we derive together through mathematics, right? So x of s over f of s, as we did for the impulse, was closed transfer function was s squared plus omega 2 zeta omega ns plus omega n squared. So x of s becomes 1 over s because of this omega n, as we did in the previous class, because you have two poles, s minus p1, s minus p2. Because you have the poles of the system like this, right? So we can again write as a over s plus b over s minus p1 plus c over s minus p2. And you can write as s in s minus p1 in s minus p2. So you're going to have a in s minus p1, s minus p2, plus bs in s minus p2, plus cs in s minus p1. This is the most trivial method to find a, b, and c. There is also residual method I don't want to teach you because okay, so this equals to if I write in the s square, so you have a plus b plus c, okay, and now if you write in s order, you're gonna have minus a p1 plus p2, okay, minus a minus ps1 p2s, so let me write clearly, A P1 plus P2, this is one S. Another is minus B P2. Another is minus C P1 in S. And the only number that we have here, for God's sake, is plus AP1, AP2. And this is the same as S minus P1, S minus P2. Obviously, this numerator equals to how much? Omega n square. Double check everything. Yeah. By saying that the coefficient of the S is 0, S squared, coefficient of the S is 0, and it's equal to how much? Omega n squared. So can I go to the next page? Yes. So A P1 P2 equals to omega n squared. Okay. So you know that P1 P2 means minus zeta omega n plus I omega d minus zeta omega n minus I omega d. From high school, you know that this is zeta square omega n square minus omega d square in I square. So this is I square is minus 1 plus omega d square. So omega d, as we did in the previous class, is omega n square 1 minus zeta square. This goes to New York. The result is omega n square. So from here you get A is 1 as expected. Hopefully this is recording right. Yeah. A is 1. Now I'm going to put here. See? B plus C is minus 1. And B P2 plus C P1, B P2 plus C P1 equals to the other side. A is 1, so it is P1 plus P2. So I'm multiplying both sides of this by minus P2 and then sum. If I do that, you're going to have CP1 minus CP2 equal to P1 plus P2 minus P2. That's right, this is 2. This is 2. This goes to New York. So you get C is equal to P1 minus P2. So P1 minus P2 minus zeta omega n plus I omega d minus zeta omega n minus I omega d, as we had here. Let me double check because I'm doing with you. You know that I hate notes. Yeah. So I multiply it by P2 Yeah. So from here you get C equals to P1 divided by this with this minus plus 2I omega d. This is C. Okay. If you put it here, you get B. So B equals to minus 1 minus C. Okay. So minus 1 minus P1 into, or we can keeping like this instead of putting here. See here, guys. I'm gonna put this here for simplicity. See here, this minus 1 minus C. So minus 1 minus P1 over P1 minus P2. So this is gonna be P2 minus P1, right? P2 minus P1 over, again, 2I omega d, because principles. So gonna be P2 minus 2P1, 2I omega d. Okay? Okay. Clear? So now we have everything. X of t equals to A over S plus B over, because A is 1. What is that? S minus P1, S minus P1 plus C over S minus P2. And the A was 1. Hmm? Can I go to next page? Yes? Yes, guys? So, X of t gonna be 1 over S. Your B was this P2 minus, and you see that, oh, you see that they share this 2I omega d, 2I omega d, B and C. So it comes out 2I omega d. Now your B is P2 minus P1, P2 minus P1, S minus P1, no P2, sorry guys, P2 minus 2P1, 2P1, plus your C was how much? P1 over this, P1 S minus P2. Understand? What? No, this is B. This is B, guys. What is B? B. Okay? Understand? Yes, everybody? So P2 minus 2P1, you can calculate these numbers, right? Hmm? And simply you see that this is gonna give you, when you go to time domain, guys, I skipped the calculations. X of t, when you do that, you're gonna apply the Laplace transform. Okay, the Laplace transform. If you do that, you get this 1, because this is the unit step. If you do the calculations, this is the answer, the final answer. So, because I don't want to waste your time, gonna be cosine omega dt plus zeta 1 minus zeta square sine omega dt. Bingo. It's the response to unit step. Actually, let me see, guys. I did a mistake here. Hold on, guys. Oh, I see. Um, oh, this. No, this is right. Okay, everything right. Yeah, okay, that's fine. So this is the final answer. This is output of the systems. Output. What is this? This is the system? Tell me. What is this? What is this? What is this? 1 unit step, input of the system. So I'm saying output minus input equals to E minus zeta omega nt cosine omega dt plus zeta 1 minus zeta square sine omega dt. Okay? Output minus input. What's that? You tell me. Yes. So this is input, this is output. Okay? So this is error signal. So your error signal is this value. So when time goes to infinity, a large value, what's gonna happen for this, guys? For this decaying term? What's gonna happen for this term? Yes, so steady state error signal goes to 0. ESS goes to 0. But with some oscillations, cosine and sine. Okay? Saying that, if I want to plot your response, and I'm going to do in MATLAB now after teaching some concepts. This is the step, this is unit step 1. input to the system. You see decaying and oscillation. This is oscillation. Here we go. This is out of the system. And the error signal is here. See what I'm saying? So mathematical proof of that is also easy. Can I go to the next page? Yeah, okay. So we know that ESS is a limit of S, f of S, 1 plus G, open loop transfer function. So it is limit of S, 1 over S, 1 plus omega n square, S square plus 2 zeta omega ns. This is open loop transfer function, guys. Open loop transfer function, as we did in the previous class. So this is 1, a limit of 1 over 1 plus omega n square over 0, infinity. 1 over infinity is 0. Okay, so before going to the MATLAB and saying that for the underdamped second order systems, if this is x, this is t, and this is the input, and this is the output of the system, there are lots of parameters. One of the parameters is this, the time that which for the first time your output crosses the input. We name this as TR, rise time, for the second order system. And this is exactly, you can feel it in your car after passing a bump. Or suppose that you're on the road and there is a step in the road, uneven step, and it's the tire of your car. Okay? After passing this, you're gonna feel exactly this. After passing and coming here. First you were here. After passing that, you're gonna feel this. I have no doubt. You have a transient oscillation, then settling down to your final position in your car. Everybody have experienced this? Yes? So, how to calculate raising time is easy. It's easy. What happens at raise time, guys? Look at here. What is the value of... Oh my God. What happens at the raise time for the x? What's the value of the x at raise time? Here is 1. Huh? Yes, 1. So at raise time, x is 1 for the first time. 1 minus 1 is e minus zeta omega n tr at raise time. Cosine omega d tr plus zeta 1 minus zeta square sine omega d tr. This is 0. Obviously, from kindergarten math, this can't be 0. Because there's a time here. So this is 0. If that's 0, you get cosine omega d tr plus zeta 1 minus zeta square sine omega d tr is 0. Saying that you can get tangent of omega d tr equals to 1 minus zeta square over zeta. Everybody agree? Yes? From here you get that omega d tr is equal to tangent inverse of minus 1 minus zeta square over zeta, and bingo, you can find raise time as 1 over damped natural frequency for any second order system. Tangent inverse of 1 minus zeta square over zeta. Here we go. So we found the rise time for the second order system subject to the unit step and is underdamped. So let me delete this. Tangent zeta. Another parameter that you can see here is this, the peak or overshoot. I am pretty sure you have experienced this a million times in your car after passing a bump or after passing a step. Peak, your body feels a peak and then comes down. Or overshoot. And in control class, one of the things that we reduce the amount of the overshoot. This is overshoot. This value is the overshoot. By controller, we want to do that. Okay, how to find that, guys? What happens mathematically here at this point? What is 0 from high school? What is 0? Yes, derivative is 0. Slope that is 0. So, can I go to the next page? So at that point, dx over dt is 0. So x was, I'm writing here, e minus zeta omega nt cosine omega dt plus zeta 1 minus zeta square sine omega dt. So dx over dt of this is 0. Okay. So dx over dt, if you calculate that, I don't want to do that, okay? And put the time tp from here. If you calculate that and implement here, you get what? You get, let me do one of a few steps, minus zeta omega n, the first and second and first, e minus zeta omega nt cosine omega dt plus zeta 1 minus zeta square sine omega dt. This is the first term, derivative in second term. Now again, because derivative of this is 0, obviously, e minus zeta omega nt, now here, minus omega d sine omega dt, because cosine is minus sine, and plus omega d zeta 1 minus zeta square cosine omega t. So this is equals to, you can factor out this e minus zeta omega nt. You have cosine and cosine, but you can simplify this because omega d zeta 1 minus zeta square. Omega d is omega n. 1 minus zeta square. Zeta 1 minus zeta square. So the answer, this is gonna be zeta omega n. Okay. So cosine omega t zeta omega n minus zeta cosine omega n. That's right. This goes to hell. Everybody agree? Yes. See what I have done? First, let me double check everything because I'm drawing with you. Cosine omega. Yeah. So omega d zeta. Yeah. So see, zeta omega and cosine here is plus minus zeta omega cosine. So this goes to hell. So the second term remaining here one is gonna be minus zeta square omega n 1 minus zeta square to sines plus omega d sine omega dt. That's right. Everybody agree? Yes. So obviously this is a constant number. You can simplify it, guys, because this is a constant number. Minus zeta square omega n plus omega d is this. Gonna be omega n again 1 minus zeta square. 1 minus zeta square. Yes. No, omega d, damped natural frequency. See what I'm saying? So no, omega dt means omega dt. Okay. See? So this is 0 because derivative is 0. Okay. So this cannot be 0, obviously, because we have a time Tp at peak time. Right? So this is 0. So sine omega dt is 0 at peak time, Tp. From high school, you know that this is sine of k pi. That's right. And the k is 0 plus minus 1 forever. So you cannot select the 0 because you have Tp 0. That sucks. So I'm setting k is 1. So omega d Tp peak time is pi. So you can get Tp is pi over omega d. Understand everyone? So the peak time, this peak time, here is Tp. Peak time is pi over omega d. You have to know this is very, even in the vibration course that you had course with me, this is very, that I was teaching as the concept of the log decay. Remember that you had with me? Log decay. But here in the control, we're saying the peak time. Now what I'm gonna do, for God's sake, you don't have to know the process, you only have to know the result, okay? I'm just gonna put it out here to find the maximum overshoot. Can I go? Yes? So x of overshoot, xp, 1 minus or peak, is E minus zeta omega n Tp cosine omega d. Tp is pi over omega d. We found it. Plus zeta 1 minus zeta square sine omega d in peak time, pi over omega d. How much is sine of pi from high school? How much is sine of pi? Guys, 0. How much is cosine of pi? Here we go. So x of peak is E minus zeta omega n. Oh my god, I'm getting older, guys. Omega n, and Tp was pi over omega d. And this is minus 1. Minus and minus plus. So xp is equal to 1 plus E minus zeta omega n pi, and omega d is omega n 1 minus 0 zeta square. Bingo. So I said peak, but I showed peak this distance, x of peak minus unit step. This is the peak that you are showing with the m maximum peak mp in control. So see, xp minus 1. I'm going to do that. I'm going to move to the other side. So xp minus 1 that we are showing with the maximum peak, okay, equals to E minus zeta pi. You see, that's a function of the damping ratio. That's it. Here we go. That we are showing in the percentage. It's minus zeta pi 1 minus zeta square. So when I say MP is a 50 percentage, it's a huge value for your car. You as a control engineer, you have to reduce this. Means you have to put MPA as 0.5. The desirable that we want to have MP is 0.25 always. Based on the requirement of your boss. Maybe your boss wants to design an MP of, I don't know, 0.3, 0.2. Saying that, I'm going to go to MATLAB, don't worry, okay? Saying that, okay, this is the input. If your damping ratio, zeta, you have very underdamped system, say is 0.1. So if you put that, your system has very low damping. You can explain this, guys. And this is not good at all. When you increase damping eventually, 0.5, you're gonna get this. I'm gonna show MATLAB, okay? This is much better. Okay? If your system shows this kind of response, this huge overshoot, you have to use, I'm gonna show you how, PD controller to reduce it. PD controller to reduce it. And your car suspension system, active suspension system of your car, like as Mercedes, I don't know, new cars, whatever, BMW, they have a controller to reduce that feeling after passing a step on the road or any bump in the road, whatever. And the whole story about the control is this. See what I'm saying? But we are not done with the parameters, because we have another control parameter that we have to, after teaching you this, then I will go to MATLAB. These are parameters, as I taught you, like as the TR, like as the rise time, TP, MP. These are parameters for transient response. Transient response for this area. But you as a control engineer, maybe your boss says you, okay, design a building for me. Building, not the car. That after earthquake, the settling time is for the steady state response. Steady state response. So settling time means that, let me show you. Okay. So, suppose you have this. Okay, this is much realistic. So, you see that we have two settling times. One of them is that when your response is 5% of that final response that you want to go to the step. Here is 5%. Another settling time is the time that you have this value, 3%. You have two criteria for the settling time. Okay, I'm skipping the math because it's gonna teach you the manifold, this kind of thing. So for 5% criteria, we name it criteria, TS settling time is, you see that in this graph has a larger value, that's right. It's gonna be 4 over zeta omega n, and if I'm not wrong, this is 2%, not 5%. This is 2%, guys. 2% criteria. Okay, and for 2% criteria, settling time is 3 over zeta omega. So based on these transient and steady state parameter of the system, now your function is to design a controller to satisfy the requirements of your boss, your company boss, design controller to give you this. You're going to tell me, are you stupid, payment? No, I'm not. Guys, see that the overshoot was minus zeta pi 1 minus zeta squared. TS settling time was over zeta omega n, or 3 over zeta omega n. But now you can understand why I got the poles of the system in zeta and omega n format. Okay, I don't care what your system is. Has mass, spring, damper, has the resistor, inductor, capacitor, has tank of the water, resistor, whatever it is that I'm teaching in ME430. That's right. See what I'm saying, guys? In this class that I'm teaching, so you see that I taught massive spring damper. I'm going to teach the RLC later, okay? So we are talking about the universal parameters, zeta omega and zeta omega. See what I'm saying? So your function is design controller, guys. Look at here. Listen very carefully, because when it comes to ME430, if you have, this is a pair of complex conjugate poles, right? If you come to ME530, this means that the poles of the system has a low value of the zeta omega, but has a high value of what? Omega d. What does it mean, guys? What does it mean physically? What is this I stands for? Oscillation part, that's right. So it means that the system is going to be like this. If I tell you guys, this system gonna behave like this. But this system, if I by designing controller, if I do this, change the poles to this, I transfer to this. This means you have a larger zeta omega that is for decaying term, and you have a low amplitude vibration. You're gonna have this. See what I'm saying? Yes? Or let me do this more carefully, because it's gonna be like this. There we go. And this is more desirable. See what I'm saying, everybody? So this zeta omega and omega, the zeta and omega, a pair of complex conjugate poles, they have meaning. Understand? So this is how we model the system when it comes to ME530. You see that how you design control for this. Okay? Everybody? So now let me go to MATLAB. For the MATLAB, okay, hold on. Yeah. So MATLAB, I want to plot both impulse and step input for the underdamped system. Okay. I'm going to share with you. Until MATLAB comes up, you know that. Let me go to the next page. X over F was omega n square S square plus omega n square S plus omega n square. For coding, you know that your num, because second order system, gonna be 0, 0, omega n square. Your then, for the unit step, gonna be 1, 2, oh, what this? 2 zeta omega n. 2 zeta omega n and omega n square for unit step. But in the MATLAB, remember that we don't have impulse, that's right. So as we did the trick previously, impulse is 1, means S multiplied by 1 over S. So this is a step for the impulse. So you're going to change the transfer function. X over the step for the impulse gonna be S omega n square in S square plus 2 zeta omega n S plus omega n square. So for the impulse, these are for a step. As we know, for the impulse, you have a new num, which is 0, omega n square and 0. See the difference between them? Okay, so let us do that. Okay. So I'm gonna say CLC clear all, close all. Now, okay, omega n of the system is, I don't know, 5 radian per second. Zeta of the system is a very undamped system, 0.1. Okay, and num 1 for the impulse. I'm writing here for the impulse. Impulse is 0 omega n square and 0. See, and then was 1 2 zeta omega n and omega n square. See here, guys, this is your num because you added s here, and then is the same. Okay, so I'm saying figure 1 step, but I'm plotting impulse num 1 and then greet. That's it. Okay, and I'm gonna say it as ME430 as the impulse and step of second order system. Okay, so please pay attention that we change this. So here we go. So if I run it, here we go. Do you see that? Impulse. And you see the system is very underdamped. You have lots of oscillation because zeta is small. Are you following me, guys? Yes? Can you see this?
Yes.
So if I say, let me check, let me do this. I want to show the difference. And zeta 2 is 0.5. See, I'm adding more damping to the system. So I'm going to say hold on, and this is then 1. Okay, hold on, and still is we are working on the impulse. So if I say this, and if I run this, oh, then 1. I'm stupid, guys. Then 2 without creating. Then zeta 2, zeta 1. Okay, here we go. There we go. See the red one, and this is more desirable. Do you see this? Then I added damper to the system for the impulse. Obviously, and when I say for the step, I have to change the numerator to the standard one that we had. Okay, for the step num2, look at here, guys. 0 0 omega n square. This is 0 0 omega n square. Now if I say I'm gonna repeat everything to the figure 2 for the step response. Figure 2 is gonna be num2 num2. That's right. And because I'm going to send it to you. Title is impulse response. Okay. Okay. There we go. Exactly this. See? For the low value of the damping, 4. And we like this in control class. In ME430, we like this response. Okay. So to validate whatever I taught you for modeling of physical systems, remember that we calculate the overshoot MP as exponential of minus zeta, say zeta of zeta 1, zeta multiplied by pi divided by SQRT of 1 minus zeta 1 square. Remember? You have in your notes. You see that? So this is when the zeta is a small value, is 0.1. Zeta 1 pi, this is the, so let us calculate that. What is that? Oh, I'm missing the, I missed it, okay. So it says that your MP is 0.72. Let me measure it, okay? From 1 to 0.72 exactly. Do you see that? Because this minus this is 0.72 almost. This minus this. Do you see that, everyone? Yes? Understand? And it gives you exactly the maximum overshoot. And even you can calculate the time of that. You can just type it here. Say time of P is pi over omega d. Omega d was omega n multiplied by SQRT of 1 minus zeta 1 square. There we go. Obviously must gives you the time is 0.63. Let us double check everything, okay? Here we go. 0.63 like that. The time of the overshoot. If you do that. Huh? Understand? And obviously for complexing and settling time based on the 5% gonna be 4 divided by zeta 1 in multiplied by omega n. Okay, based on 5% criteria. It's 8 seconds settling time and must be 8 seconds. See, exactly here is 5%. If you this distance, let me magnify it, guys. This distance is almost 5%. Okay, guys, understand everything? And before going ahead for the ramp input for the next class I'm gonna go to the Simulink and redo these, because now you know how to do it. It's gonna be quick, a few minutes, and then we're gonna continue talk. Okay, everybody? Thank you too, guys.